And that is the main purpose of this course. And then we also need to know some basic theorems, which we didn't learn in geometry, okay, in your school geometry class. All right, so the first thing I want to do is Pythagorean theorem. Sorry, this is the wrong spelling. Pythagorean. Yeah. Matthew, do you know how to prove this?
Do we do it geometrically?
You have to, right? So if you have a right triangle like this, I mean, if you learn the geometry in school, the teacher must have shown you how to prove this, right?
Yeah, there are many ways.
Here's A, here's B, here's C. And the theorem says that A squared plus B squared equal to C squared. Agree? Allison, do you know how to prove this? Did you learn geometry in school?
No.
No, not yet. Okay, sorry. So most of you are 7th or 8th grade, right? I thought that, you know, you are not learning geometry in school, Allison?
Not yet.
How come? You finished the you finished the algebra 1, right?
Yeah, we're doing geometry next year or this year.
Oh, I see. You just finished algebra 1 right now.
Yeah.
But then you started with me on algebra 2, a little bit too early, right? But anyway, so you learned very well. Okay, so that's fine. Okay, so the idea of proving this is very simple. Okay, so in school geometry class, the teacher should tell you that you see the C square should be thought of as a area of a square. Do you agree? So therefore, we need a square which has a side C there. Okay. For that purpose, we're going to extend this line here. I mean, sorry. We're going to build a square with a side C. So that is, let's see here, right? We're gonna build a square of side C here, okay? So this is a square. So okay, so this is a square here. The side here is a C, yes. So our goal is to show that A squared plus B squared equal to C squared. For that, maybe we can do the following. We can extend this side here, and let's notice this. Okay, so Allison, do you know this? Do you know that these angles add up to 180 degrees? Do you know this? The in the triangle ABC.
Yeah.
You know that these three angles, interior angles, add up to 180 degrees. Do you know this?
Yep.
You know this. Okay, very good. How do you actually prove this? So
you can draw like a line that's parallel to the base of the triangle, starting from the very top point.
Okay, good. Then?
Since we know the two lines are parallel, you can see that that we have like certain congruent angles. So like the angle at the bottom right of the triangle is equivalent in measure to the top right.
This one, you mean this one? You mean this one?
Yeah.
Okay. And so therefore this angle equal to this angle, and therefore this angle here has to be equal to.
Yeah, to the other angle at the bottom right
Yeah.
corner.
We also know this. Okay. Yeah, that sounds very good. Very good. Okay, so a different way to do this. I mean, yeah, this is good. Okay, so what you can do is that you could just always start from right triangles. So you could break the top angle into two pieces. Okay. Now look at this thing here. Notice that. So this angle here, because this is right angle, right? This is right angle. So and if you draw this, you can also see that so this is right angle, and this is also a right angle. So this shows this angle and this angle are complementary, right? So they add up to 100. These two add up to 90 degrees there. Okay, is that right?
Yes.
Now, if you look at this triangle here, I mean, this angle is also right angle, right? Because it's a rectangle. And you know that in the rectangle, the diagonals will divide this rectangle into two equivalent what? Two congruent by symmetry, right? By symmetry. This will divide this into two congruent triangles. Do you agree? And therefore, this angle here has to be equal to this angle. Yes, do you agree? Because these two triangles are completely congruent. So that's why you would have these two angles are the same. But this is by the geometrical symmetric argument here. It's very hard to do geometry, okay? So you should know that in Euclidean geometry, the only way to do it rigorously is doing this without any figure, okay? So it's dangerous, all right? Because if you use figures, when you do the argument, sometimes you could make error, okay? So that's why in the Euclid, the original postulation, he has these, you know, these, how many axioms? 5 axioms, is that right? So all done without what? Without a geometric picture there, all right? So you can do this, and so we know that the sum of the interior angles for triangle is equal to 180 degrees. All right, so then we can do this. And we notice that because this is a right angle, so we know that these two angles are complementary. This angle and this angle, right? They are complementary, which means they add up to 90 degrees. Let me call this as alpha and beta. So alpha plus beta equal to 90 degrees, yes? And then you can do the same because this is a right angle there, and therefore this angle should be alpha again. Do you agree? So this angle should be alpha again because they add up to 90 degrees there. So this side is A here, okay? All right, from there, you can see that the idea is that, how about this? I'm gonna extend this line segment here. Let's assume that A is less than B, okay? So we do that. So we're going to shrink this a little bit so that we extend A, the side length A to a length B, okay? We're gonna extend it. My goodness, so this is hard to draw here. Okay, then we're going to construct another right triangle this way. So this picture doesn't look like right here. So let me extend a little bit further. Oh gosh. So then we have this angle here. Now, now this side now becomes the B. So this part here is B minus A. Do you all agree? We just extended we extended the side A to a line segment of length B. So what's extended was B minus A there. Now, because this angle here, alpha is complementary to beta, and if you draw the angle here as beta here, then extended, you should get the right angle there. You agree? So, and because this hypotenuse here is C, you can see these two triangles are essentially the same thing. Or they are congruent, right? When I say essentially, meaning that their corresponding sides are the same. And you can build this, you can keep building this. So what we're gonna do is that we're going to extend this again. And then we're going to draw this line segment there. All right, so then we're going to extend this again. Okay, and I think this is not the right angle yet. Okay, so if you do it carefully, and you will see that these sides are all equal to C for the hypotenuse. And this side is B minus A, and this side is A here, and you see that you have a 4 congruent triangles. So this side is B minus A. All these are right angles. Okay, so allow me not to give you the complete proof, because if I do the argument, I would have spent almost like 15-20 minutes just on this picture. Okay, using this picture, you can see that the total area of the square can be split into 4 right triangles, which is 4 times 1/2 of A times B, agree? Because each right triangle has a length, side length AB, and therefore the area is 1/2 of the base times height. Then you have to add the inside. The inside is B minus A quantity squared, you agree? And therefore, if you add this up, you get A squared plus B squared. Because the 2AB, negative 2AB cancel. So this is how you prove the Pythagorean theorem, right? Now, the reason we want to go through this is because the entire geometry, trigonometry, and so as long as the geometric related topics is all coming from Pythagorean theorem, okay? So this is a so-called mother theorem for the modern mathematics. Without this theorem, then there's no modern mathematics. Okay, seriously. So, and we need to absolutely understand this. Okay. Next one, we want to do similar triangles, and this one is hard. Okay, because in the school, the teacher will never teach you this, right? Matthew, do you agree?
Yeah.
So why do I say that? Why the teacher never teach, right? Yeah. What was the definition of? What was the definition that 2 triangles are similar? A, B, and C here, right? And then you also have a triangle A prime, B prime, and C prime, agree? Let me call the corresponding sides are A, this is A prime, and the B, and this is B prime, and the C, this is C prime. Okay, you should know that these are, let me call the angle here is alpha, beta, and gamma. This is alpha prime, beta prime and gamma prime. Now, in the school geometry, we said that the triangle ABC is similar to triangle A prime, B prime, C prime. If what? If the corresponding angles. So this similarity is defined in terms of the order of the vertices. Okay. If first of all alpha equal to alpha prime, beta equal to beta prime, and gamma equal to gamma prime. Do you agree? So you need this. The three angles are congruent. Is that correct, Matthew?
Yeah.
What else did the teacher define? Did the teacher say that? Did the teacher prove this theorem? I bet they don't. Okay, they didn't.
No.
That if triangle ABC is similar to triangle A prime, B prime, C prime, or rather say this is true if and only if A over A prime equal to B over B prime equal to C over C prime. Did they prove this theorem?
No.
Well, how did they define the similarity in school?
They said that the triangles are similar if their corresponding angles are congruent,
And
if they are similar by a certain scale factor.
yeah, so in other words, this is basically just built in their definition. Okay. I saw some of the geometric books, they just define this to be the same. Either this or both, but that's not the case. Okay, so in general, the definition should be just one of this, and this is actually a theorem. So to prove the theorem is hard. Okay, it's hard to prove. First of all, we should notice this. Recall the area of a triangle is what? What is the area of a triangle? If you call the base here as A, the altitude here is H. What is the area?
1/2 base times height.
Right, so the area of the triangle is 1/2 of A times H, right? Can you prove this, William?
So I think we can split the base.
We're gonna just build a rectangle here, right? Do you see this?
Yes.
So you see, because it's a rectangle here, and these two triangles are congruent, right? They are the same.
Yes.
You just cut it and you can regroup them together. So they are the same. So that tells you that the area of this part is the same as the area of this part, okay? And similarly, the area of this part here is the same as the area of this part, okay? Right?
Right.
That's clear, right? That is clear. We don't have to give a very logical proof here. It's kind of a very intuitive here. All right, so because of that, you can see that this area here is just what? Is just a
1/2
same.
the area.
Yeah, these two area adding up. The area of these two triangles adding up is the same as this one. So therefore, we know that area of a rectangle is base times the width, right? And that's by the definition, okay? By definition, the area of a rectangle is just equal to the base times the width. It's a definition. There's no need to prove this. So therefore, the area of the triangle is just half of that. And that's the only thing we use at this point. Okay, we know this. We know that area of a triangle is 1/2 of base times height. Addison, you haven't learned geometry, but you know this, right? Yes? Addison? Left? Emily?
Yeah.
Emily? Yeah, we all know this, right? Even if we didn't learn geometry before, but we all knew this, right? Is that correct?
Yeah.
Now, let's prove this. Okay, prove the theorem now. We prove it's if and only if condition. What does that mean? That means if they are similar, then this ratio relation will be true. And conversely, that if the ratio relations are true, satisfy this equality, then the two triangles are similar. And don't forget our definition that two triangles are similar if the corresponding angles are congruent, okay? Now, to prove this direction, so you need to prove two directions. So assuming that the triangle ABC is similar to triangle A prime, B prime, C prime, that means if the corresponding angles are all congruent, then you want to show the ratio relation must be true, okay? Okay, so this direction says, so this says we are using this as a condition to prove the other one, okay? So assume that alpha equal to alpha prime, beta equal to beta prime, and gamma equal to gamma prime, okay? Assuming the corresponding angles are all equal. Then we can do the following. We can glue the two triangles together. So I can think of this as A equal to A prime. So we group the two triangles. A equal to A prime. Here's B. Here's a C here. Maybe we do this. Maybe we do this way. So we call this B and C here. We call this B prime and C prime, okay? Now, because this angle, so alpha equal to alpha prime, they are the same, right? And the beta equal to beta prime, okay? So this is a beta. I mean, did I write the 2B there? This is C here. So they are the same. If they are the same and this angle equal to this angle here, as you can see, then what can you say? So since beta equal to beta prime and gamma equal to gamma prime, we see that the two lines BC is parallel to E prime, C prime. Do you agree? Are you all with me on this?
Yes.
The many people who didn't learn the geometry in school, do you know this is true? What does parallel mean? Parallel means that they never intersect, okay? The two lines are never intersect. But if the angles are the same, you see that they can never intersect. Because if they intersect here, you see if they intersect eventually, right? Then what? Then, so if they intersect here, so this is the line we are talking about here. Okay, this is the line we're talking about here. If they do intersect, you can see that the angle here, or rather say this angle here. So this angle would be equal to this angle here, okay? And so therefore this angle here would be equal to what? This angle here would be equal to the, let me call this as theta. And this is, so this one was gamma, right? Gamma prime. I mean, actually, we knew that the gamma equal to gamma prime, so let's not using a prime there. We knew this is a gamma, and we also know this is a gamma here, agree? So therefore, this angle here would be 180 degree minus gamma, agree? Yes?
Yes.
But on the other hand, you can see that this is a 180 degree minus gamma. But so you know what, this angle here would be equal to this angle, yes? But how can that be? Because the interior angles add up to 180 degrees. But here, if you add gamma with 180 minus gamma plus theta, you would get 180 degree plus theta, which is greater than 180 degree, right? So that's not going to happen, right? So you know what's if the gamma, if these two angles are both are gamma here, then these two lines can never intersect, which means they are parallel, okay? So this is just a obvious argument, but we do want to give you a reason there. So this says if these two are the same, then the BC must be parallel to B prime C prime, right? They are parallel. So in other words, if the two triangles are similar, you can see if you glue them together with a one angle to be congruent, then the two bases must be parallel, okay? All right, so if they are parallel, that means what? What does parallel mean? Parallel means that the altitude here from B to this BC, B prime C prime, from C to the B prime C prime, then these two altitude must be the same, okay? If they are parallel. Are you with me on this?
Yes.
Yes, okay. So now let's try to see. So now let's try to see that what we can do to show that the ratio relations are true, okay? So what we're gonna do is build this, this triangle here, extra triangle. Now the triangle we're gonna build is this triangle here. And another triangle like this, okay? So, since the altitude or the height of both, so of both triangles, both triangle B prime, then BC, and the triangle C prime and CB are the same, agree? Do you agree? Because the BC is parallel to B prime, C prime, that means the altitude from C prime to BC, B prime to BC are the same, do you agree? They are all equal to H. Does that make sense? Make sense to you?
Yes.
Okay, so this tells you that the area of the triangle, which is, I use a bracket to indicating the area. So the triangle B primes BC is equal to the area of the triangle C prime CB. Agree? They are the same. Yes? We are using BC as the base. All right? They are the same. Okay. And so they are the same. That's very important. Now let's consider the ratio relations. Now consider these relations. Triangle A, B, and C. Looking at its area over the triangle. So ABC here over the triangle B, C, and C prime. What is this ratio? Can anyone tell me? We're looking at the area of this triangle and area of this triangle. What is their ratio? Let's turn this this way. So this is A, B, and C, right? And you got so let's use a different letter here. So this is so this is a C here, right? And then we have we have so A, B. This is B, and this is C here. Sorry. BC is the, okay, so this is the wrong side here. That's a C here and a C prime here, and this is A. You agree? What is the, still wrong. So this should be C and this should be B, agree? Turn this out. Now, if you do the area of this ratio relation between, if you find the ratio, what is the ratio of these two triangles, area of these two triangles? Can anyone tell?
It's AC over CC prime.
That's right, it's AC over CC prime, do we? Because these two triangles share the same altitude here. You see this? If they share the same altitude, this is H. Then for the left-hand side, the area is 1/2 of CC prime times H. The other side is 1/2 of AC times H. Do you agree? If you take the ratio of these two, of course, it's just a ratio of these two sides. So this side and this side, okay? Let's see if everybody understands this. Alvin, do you understand this so far?
I think so.
Yeah, I think so. Okay, very good. Allison? Can you talk? Allison? All right, so let's see. Omar, do you understand so far? Rebecca, do you understand so far?
Yeah.
Okay. Let's see who else. Let's see. Okay, so I don't see. Okay, Ria, do you understand this so far?
Yeah.
Okay, so you learned the geometry in school, so you shouldn't have too much trouble, right? Have you learned the geometry in school yet?
Yeah.
Okay, very good. But this proof is not given in the school geometry class, is it?
No.
No. Okay, so usually teachers don't prove theorems because maybe it's a little too hard for this geometry class. But you see, if you don't prove the theorems, then we basically do not know anything. Okay, we do not really understand anything. So, okay, this says you have such a relation, right? Let's try another one. Let's try triangle ABC over the area of the triangle B prime BC. What is that ratio relation equal to? This time you tell me. We are talking about, right now we are talking about a different ratio relations there. This time we're thinking of this one and this one.
The ratio is AB over BB prime.
Yeah, so it's AB over BB prime. Do you agree? But do you know that this is the same as this one, right? They are the same. What about this one? These two are also the same, right? We just had that, yes? Right? So let me call this a star here. So by star, we know that the AC over CC prime equal to AB over BB prime. Do you agree? Yeah, the same. Yes? Okay, so that's great. It's already giving us this. It's already giving us that. So this is same as saying that AC over AB equal to CC prime over BB prime. Do you agree? So we already knew that this length over this length equal to this length over, sorry, no, that's not what I mean. I mean that, so this so this over this is equal to this over this, okay? We already knew this relations. Do you agree? Actually, we actually prefer the other way. So I shouldn't have this because this is not what we really want. Okay, so let's erase this. We don't need this. So in other words, even though it's true, but that's not the best equality we want. So let's turn this upside down. Let's turn this CC prime over AC equal to BB prime over AB. Do you all agree? Which, if the ratio is the same, then we can turn this upside down. It's still equal. And then I can add in 1 to both sides. Do you all agree? Can I add 1 to both sides? It's
Yes.
still equal. Why do I add 1 to both sides? Well, if you add 1 to both sides, you see what you get. We are getting, the base here is AC. What's the top? AC plus CC prime, yes? AC prime. The base here is AB. The denominator, the top is AB prime, right? But don't forget, A is the same as A prime. So we put A prime there, yes? Right? A and A prime are the same. So we put A prime on top. And this way I proved that if the two triangles are similar, I can show that the ratio relations are true. And then I only proved 2 of those. And similarly, you can prove the other 2. Do you agree? Are you with me?
Yes.
Can you prove the other one instead of proving these 2 ratio relations? So let me say similarly. Okay, similarly, A over A prime equal to B over B prime equal to what? And A over A prime equal to C over C prime. Do you agree? So you can do that. All right, so let's say this is the proof of one direction. And you know what? To prove the other direction, it's even harder. Okay, it's even harder. So I will not do it for you right now because I let you figure this out yourself. Okay, so I mean, it's harder to figure out, but I'll let you to ponder on this. So in other words, in your school geometry, you're not, this one, your school teacher must do. Okay, so if the school teacher doesn't do this, okay, so if the school doesn't do this, that's a joke. You are not learning geometry at all. You are learning nothing, okay? So this is the very basic picture of in geometry. The school teacher must do it, okay? Now for this one, the school teacher don't because it's hard, okay? School teachers in general will have a hard time to prove this themselves. So therefore, do not expect the teacher to prove this. But the other direction is even harder. So using this to imply the angles are congruent will be even harder, okay? So that one we can prove it. But I just don't feel like I want to do it because it will take too much time, okay? I give you a flavor of one direction. And then now you know that if the triangles are similar, then the ratio relations are the same. And there is a theorem which tells you that if the ratio relations, if the ratios are of the corresponding sides are equal, then you can also prove their angles are the same, okay? And that can be proved. Matthew, it's a good exercise for you. See if you can do it yourself, okay?
Okay.
All right, so now we're going to move on to another so-called equivalence relations among the similar triangles. Okay, so here's the theorem. So the following are equivalent. The first one is triangle ABC is similar to triangle A prime, B prime, C prime, okay? Now notice that when we define the similarity like this, we assume that the corresponding angles are the same, okay? So this is a ABC here. This is A prime, B prime, C prime, okay? If this is alpha, we don't want this to be alpha here, okay? So this is not similar. You understand? So to be similar, you need what? If you write in this order, that means the angle here must be also equal to alpha. So alpha equal to alpha prime. They must have the corresponding angles, okay, according to the letters. Remember that? This is a convention in similar triangles, okay? So In the future, when you write some of the triangles, you have to make sure the letters are matched. Okay. The second one, as we proved. So A over A prime. Let me use letters to indicating that. So it's AB over A prime B prime equal to AC over, what is that? What's at the bottom? AC over what?
A prime, C prime.
Yeah, you have to match the letter. And then?
BC over B prime C prime.
Right. So you have to match this letter, okay? And the third one is called a side angle side condition. So the following are equivalent. Any one of these conditions hold, and these two triangles are similar, which is if, okay, AB, let's do the angle first. If alpha equal to alpha prime, and started from that angle, so you get AB over AC equal to A prime B prime over A prime C prime. So you have this, here's A, B, and C here. And here is A prime, and this is C prime, and this is B prime. And these angles are equal. Okay, so the alpha equal to alpha prime, and the ratio of the corresponding sides, just one pair will be equal. So this is so-called a side angle side condition there. They are not congruent though. What we mean here is that the angle side angle, I mean a side angle side, this means that the corresponding ratio are the same. Okay, so this condition is extremely useful, right? All right, so that's the theorem. And this theorem becomes just important. Okay, so the teacher don't prove this theorem for you. Okay, teachers don't prove this theorem for you. So what we do is that I want to show you that if this is true, clearly 3 is true, right? So 1 and 2 are equivalent. We already proved this. We already proved 1 implies 2, okay? You all agree? Just prove. Now, what we're gonna do next is to show that so we want to show that 2 implies, let me do this. Let me do 3 implies 1, okay? And then I leave you to show, so 2 implies 3 will be left to you as exercise. Okay, as exercise. Now, so 3 implies 1 is important. So this is the one which we really want. Okay, we want to show that you need one angle to be equal, and you also need the 2 sides about this angle have the same ratio. And these 2 triangles are similar. Okay, so this is important. So how do I prove 3 implies 1 then? This method here is an important method called the unification method. Okay. So what is the unification method then? Well, suppose I have these two things here, A, B, and C here with the angle alpha. And we also have A prime here and C prime here and B prime here, okay? Now, with the same angle there, alpha here, right? Now, let's complete the first one as a triangle. And then we know there is an angle beta here, right? Now, the unification says this. We're going to build another we're gonna build a angle beta here because, you know, this entire real line you can build like a 0 to 180 degree, any angle you can build, right? So in particular, I can measure angle beta here. Then we draw the line to complete this. And it may not hit C prime. So let me call this point hits is C double prime on the side of AC prime. Does that make sense to you? The C prime is here and the C double prime is here. So we don't know where it is. But then by the fact that the interior angles add up to 180 degree, so this angle is gamma would imply this angle is also gamma. Do you agree? So what we do is that construct C double prime on the line A prime C prime. It may be outside of could be outside of the AC prime. Could be here, right? Could be here. But anyway, it's somewhere on this line, right? Okay, construct C double prime on this such that the angle, or rather say, just say such that triangle ABC is similar to triangle A prime, B prime, and C double prime. Do you agree? So this can be done, right? This can be done. You agree? William, do you agree? This can be done.
Yes.
Anyone else? Alvin, do you agree that this can be done?
Yes.
Yes. Okay, so it's clear. All right, so because of this, so by the theorem, 1 implies 2, which we already done, right? We proved. So we have this, we have AB over A prime B prime equal to AC over A prime C what? AB over A prime B prime. AC over?
C double prime?
Right, it's a C double prime there because these two triangles are similar, not with the C prime there. All right, so, but you see this way, but we are given what? AB over AC equal to A prime B prime over A prime C prime. So this implies what? You see, these relations can be rewritten in this, right? As AB over AC equal to what? A prime B prime over A prime C double prime, right? So that means A prime C double prime equal to A prime C prime. Do you agree? Are you with me?
Yes.
What does this conclude? This length equal to this length. What does this conclude?
This concludes that basically triangle.
No, we don't need the triangle. This is A prime, this is C prime, and this is C double prime. This length equal to this length. What does that conclude?
C prime and C double prime are the same point.
Yeah, so this says C prime must be equal to C double prime, right? So this is the argument called unification. We don't know where the C double prime is, but we're going to force the C double prime equal to C prime by the what we proved earlier. 1 implies 2, we just proved. Do you agree? Then 2 implies 3. We're going to use an exercise, but 3 implies 1, we proved it, right? We just proved. So now what we proved is this: 1 implies 2, 3 implies 1. If I can prove 2 implies 3, then you know that all these 3 are congruent. Do you agree? So this is a very good exercise for you. Okay, so now you can prove it. If you directly prove this, it's hard. But if you prove from here, it's a lot easier. Okay, because we already given a what? We already given an angle. Okay, if you don't have any angle, it will be difficult to prove. But if I already have an angle, then it's fairly easy to prove. 2 implied 3 is, okay. So in other words, if you give an angle and, so I shouldn't say if, okay, so I just said this, all right? So 2 implied 3 is this. Suppose the ratio relations are true, all right? Then you show this. Whenever you have alpha equal to alpha prime, you want to conclude that AB over AC equal to A prime B prime over A prime C prime. Okay, so that's the 3 conditions. Okay, so this is a conclusion of the topic on similar triangles. So later on, we're going to use this theorem extensively. Now, let me know, how do you think? As I told you that this is a not easy course. Okay, so so for people who are in the more advanced courses, then you should feel comfortable, right? Ria, do you feel comfortable so far?
Yeah.
So do you feel like the proof is hard, or is you can follow every single line, or some part of it you cannot follow?
Most of it.
Yeah, but you should let me know if you have any place you don't quite understand. Okay. So Emily, how do you think, Emily? Is it very hard for you?
No.
No. Do you follow all the tiny bit of the details?
Yeah.
Okay, very good. Anybody else? Let me ask Athar. Athar, can you hear me?
Yes. Yeah.
Yeah. How do you think? How do you think this proof here? Are they too hard for you, or is it okay?
No, it's not that hard.
Okay.
Yeah, so far.
Yeah, very good, very good. So, but you see that we are jumping a little bit for many of you. Okay, so some of you are even basically trying to learn the very basic algebra, and now this requires a lot of understanding the logic reasonings. Okay, so pretty hard. I would say it's pretty hard. Okay, so let's move on to the next topic. It's about inscribed angle theorem. Okay, and today we're going to basically learn 3 types of theorems. So one is on the right triangles. Okay, and let me give you a theorem, which is called a projection theorem, which tells you how to use the right triangle and the similar triangles to solve some right triangle theorem, right triangle problems. Okay, so it's not really a hard theorem, but it's just very simple stuff. Okay. Now, suppose I have 2 right triangles. Suppose I have a right triangle, okay? So not 2 right triangles, just 1 right triangle here. So this is right triangle, okay? This angle here is 90 degree here. Then we call this B and C here. Let's project from A to the BC. And let's call this angle here as 90 degree there. Okay, so this is right angle. So it's projecting as altitude. Okay, let me call this point as a D here. Okay, so if triangle ABC has angle A equal to 90 degree. It's a triangle. And AD, so and D is on BC with AD perpendicular to BC. So this altitude. Then you have the following theorem that BA square, okay, so the square of this side is equal to BD times BC, and CA square equal to CD times CB. Oh, I'm sorry, I made errors here. BD times BC, CD times CB. Okay, so this one will be reproved next time using different method here. So, do you understand this theorem? Do you understand this theorem?
Yeah.
Yeah, if you square this side, it's equal to this length times this length here. If you square this side, then it's equal to this length times this length. You agree? And if you learn the power theorem, power point theorem, which we'll do next time, then this is a trivial case. Okay, so let me prove this. But this is useful in math counts, because in math counts you only deal with the right triangles there, so that you don't have to trace the similar triangles in other words. Okay, so the proof is this. We know that this angle is just a gamma there, right? Now this angle here is beta, right? Now because this is a right angle, this is a right angle, so since the angle A equal to the measure of angle A is equal to 90 degree. Then you get beta plus gamma equal to 90 degree. And therefore the angle, this angle here would be equal to gamma, right? So angle BAD is equal to gamma as well, right? And angle CAD is equal to beta again, yes? Okay, are you with me on this? No problem, right? Because this is a right angle there, yes? All right, so because this is true, then we do have a similar triangle. So we have what? So the triangle BAD is similar to triangle DCA there. Are you with me?
Yes.
And the triangle CAD is similar to triangle CBA. Do you agree? No problem, right? Because these angles are beta, this angle is beta. So this is the same angle gamma there. So CAD, so gamma, beta, then right angle. And CBA, so gamma, beta, right angle there, right? That's the order of this similarity. Okay, so because they are similar, so we have BA over BC, right? Equal to BD over BA. And this implies that BA square equal to BD times BC, okay? And similarly, CA over CB equal to CD over CA. And this implies CA square equal to CD times CB. And so we have this projection theorem. So it's not, it's really not a big deal because it's all about similar triangles. But the point is that sometimes you can save yourself a few seconds there, right? William, how do you think? I can save this a few seconds because I don't have to trace the similar triangles anymore.
Yeah, it just determines the ratios of the different triangles.
That's right. So basically it's about this, ratio of the similar triangles. But the point is that if you know the theorem, you don't have to do that. In math counts, maybe it's going to help you, right? Because in math counts, when you do the countdown, you just need what? You just need you just need what? You just need the speed, right? You need the speed, a few seconds. You just need a few seconds there. Yes. All right. So actually, I missed the relations about the AD. You agree? So you would also have AD over CA there. Yes. You could also have this part. And for this one, I missed another one, which is AD over BA there. Okay. I missed this. So in other words, when you use the theorem, you are ignoring the altitude. You agree? Okay. So this is the projection theorem, which is sometimes useful. But next time when you learn the PowerPoint, you don't really need this. Okay, this is just a simple consequence of the PowerPoint. So I will come back to this next time. Are we all comfortable so far?
Yes.
So I need to erase this page. So next topic I'm going to do is new to you. It's called the inscribed angle theorem. So, so what we do, first of all, we need to know what is an inscribed angle. So suppose you have a circle, okay, and you have a center there. That's a center is called O here. And you have this angle. Let me call this as B and C here. Now, what kind of angle is this? What do we call this kind of angle? So the angle COB is called what? Is it called a central angle? Do you agree? Do we know this? Do we know this?
Yes.
We do know this, right? You learned geometry apparently, William, is that right?
Yes. I learned it when I was in 7th grade.
Oh, okay. That's really good. How about you? Ria, you learned geometry, right? You finished geometry in school. Yeah, so then you know this as well, right? Emily, you haven't learned geometry, have you?
No.
So do you know central angle then? Have you seen this before? Central angle.
I think once or twice.
You saw this, right? But do you do math counts?
Yeah.
Yeah. So if you do math counts, you should know this, right? You do know, you do know circles and then central angles, right? Measure of the central angles. You know this, right? How about this one? How about do you know that if the two angles like this have the same measure here, what can you say about this one? B prime, C prime. What can you say if the two angles are the same? And this chord here is what? The same as this chord, do you agree? This is called the symmetry of the unit circle. Do we know this?
Yes.
Okay. So yeah, if you have the same central angle, then the chord subtending this central angle is the same. And then similarly for the arc length, right? For the arc length, look at the arc length here. So this arc length here is the same as this arc length. They are of the same length there, right? All right, so this is the central angle. Now, what is the inscribed angle? Do you know inscribed angle?
An angle that has the vertex of the angle on the circle.
That's right, very good, very good. Yes, so that means you do know this. Did you learn geometry in school?
Yeah.
You learned, okay, sorry. There are people who haven't learned geometry yet. So, all right, so the inscribed angle is this one. This is called inscribed angle. So let me call this point here as A. Are points.
Dr. G, I think it's lagging a little.
I'm sorry?
The screen was lagging a little. Like we
I
couldn't
know.
hear
And
you.
so what do you mean? The screen is what?
We couldn't see you like right on the screen for a while, and we couldn't hear you talk either.
So there was unstable internet connection there. Can you do it? Can you hear me now?
Yes.
Yeah.
Okay, good. All right, so suppose A is on the circle O, and B and C are points on the circle. Then the angle A or CAB. CAB is set a inscribed angle. Okay, so inscribed angle. Does that make sense to you?
Yes.
Okay. Now, what's the relation between the central angle and the inscribed angle?
An inscribed angle has a vertex on the circle, while a central angle has its vertex as the center.
What is the relation between COB and the CAB?
COB is twice the measure of CAB.
That's the theorem. That's the theorem called the inscribed angle theorem. Okay. Now the measure of the CAB is 1/2 of the measure of COB. And this is called the inscribed angle theorem. How many people have seen this? Let's see. Emily, have you seen this before? Emily, yeah?
Yeah.
Not seen this. You seen this before? How about Ria? Have you seen this before?
Yeah.
Yeah, you learned the geometry. You have to. Rebecca, have you learned this before?
Yeah.
Well, apparently you learned geometry already, right, in school?
Mm-hmm.
Oh, cool. How about you, Alvin? You know this, right?
Yes.
For people who, how about you, Addison? Can you talk? No? Okay, so people who haven't learned this from school, just forget it. Just try to learn it here, okay? So don't worry about your school geometry. As you can see that I prove everything from scratch, right? I don't rely on your school knowledge there, okay? I did everything with reason, with explanation there. All right, so the Rebecca, can you prove the theorem?
I
you-
didn't learn how to prove it though.
You did, yeah, school teacher didn't prove it, right?
No.
No, okay. Matthew, how about your school teacher? Did they prove it?
No.
No. Okay, did anyone know? Forget about school teachers, okay? So in general, you know, we know in this country, I don't know why the teachers don't prove theorems. It's really a big mistake if you go to college without knowing the basic reasoning skills. That's going to be very, you're going to be very weak in logic, all right? So let's forget about school teachers right now. So let's just say who can prove this theorem. Can anyone prove this theorem? Matthew, can you prove this theorem? You should have learned this before.
Would you just draw a line from A to O and then just use angles?
Right. So very good. So I'm going to prove it here and in the future. So every single theorem I proved in class, you are assumed what to be able to prove next time. Is that a little bit too much for you?
Yeah.
Emily, do you think it's a little bit too much for you, Emily? If I require to prove theorems. I mean, the theorems I proved in class, I require to prove it yourself next time. Is that possible? I will send you the video recordings. Okay, I did record this lesson. You can review it again and again. Do you think it's possible? Maybe hard, right? Emily.
Yeah.
Is that too much for you? Too much a requirement for you? But anyway, so even if you cannot prove it, reproduce every single thing, you still can go on. But it's just not as you know in depth as I would require. Okay, like Kenan, do you think you can reprove everything after reviewing the theorems? Kenan?
No, probably not.
Yes or no?
No.
No, it's
No.
too hard, right?
Yeah.
Is that too much? It's too much. Okay, sorry. How about you, William? Do you think you can reproduce all the proofs yourself?
I think so.
Oh, okay, very good. Okay, Alvin, do you think you can reproduce all the proofs?
Not really.
Not really. Okay, so it does take some time. Okay, so for you to get comfortable with this kind of a class, the first time you probably cannot, but later on we're going to repeat this, recycle this material. Okay, so eventually you should be able to get it. But anyway, so you know that there is what all these theorems can be proved, right? When you listen to me going through the proofs, it wasn't that hard, right? Emily, do you think? How do you think? When you listen to me, it wasn't that hard, right?
Yeah.
So in other words, it's just that you yourself to prove it will be a little hard. But in this course, you know that all the theorems, later on you have to, we have to discuss in class. Everybody has to contribute, okay? But right now, at the beginning, I'm going to do a few, the entire talking for today's lesson. Next time, you're going to start with discussing the homework solutions and so on, okay? So let me prove this for you. So we do the proof for the cases. So the case one is this. Because the inscribed angle, there are many, many different cases. The first case is this. We're going to have a circle here. This is a circle. And your inscribed angle passing with one side passing through the diameter, like this. Here is A, B, and C here. And your center is here, that's O, okay? Now, because it's a circle, O is the center, that tells you this is radius, you agree? Yes? Do you all agree? This is radius, right?
Yes.
If you have a triangle with the same leg there, same leg there. What can you say about this triangle? If ABC with AB equal to AC, what kind of triangle is this?
It's an isosceles triangle, and
Right.
its base angles are congruent.
Right. So this implies that this is isosceles, right? How do you spell this? Isosceles. Okay. Now, Emily, you know this, right? Emily?
Yeah.
So this implies what? The angle ABC is equal to the angle ACB. Do we know this? These two angles are equal, yes? And these are actually equivalent, okay? So AB equal to AC is equivalent to say that angle ABC equal to ACB. William, you ask yourself and see if you can prove this yourself, okay?
Okay.
Okay. So, all right. So because this is isosceles, therefore what? Therefore that this angle equal to this angle, yes? So that means, so the angle OAC equal to angle OCA, yes? Do you agree? The central angle, so OAC, OCA. So OAC is the angle which is angle BAC. Do you agree? Or CBA, it's the same. Do you agree? It's the same. That's the same as CAB. It's the same thing. Now, so that tells you that what is this angle then? So this implies the angle COB is what? Is equal to this is a triangle, right? OAC is a triangle. The angle BOC is the exterior angle, okay? We know that the exterior angle is equal to the sum of the two angles and not next to it. Do we know this? So this implies this is the, let me just write it down, okay? So since angle BOC is the exterior angle, okay? Angle of the triangle OAC. This implies that the measure of the BOC is equal to what? The angle OAC plus angle what?
OCA.
OCA, yes. So which is precisely equal to twice of the angle BAC, agree? So that's the first case. So that means the central angle is twice of the inscribed angle because these two angles are the same, yes? Using the exterior angle theorem. That's case one. What is case two?
Where no parts of the angle pass through the center of the circle.
Right, so the case two is this. We have this circle, and we have this is the case. So this is the B, A, and C, right? Then we also have a BOC there. How do I prove this? That's case two. Now, there's a general principle in geometry. In the circle, in the triangle, what's the most important line in the triangle?
The sum of its angles is 180 degrees.
Yeah, we are talking about the most important line in the triangle, line segment. What is the most important line in the triangle?
The hypotenuse.
There's not a right triangle here. This may not be a right triangle.
The
Most
altitude.
important, it's altitude. Yes, very good. Who said that? Is that
Me.
Ria?
Rebecca.
Alison? Rebecca, very good. So this is the one. Yeah. So this is the most important line. Why it's the most important line, Rebecca?
It's because first of all, it could create a triangle into a right triangle, and you use it to determine the area.
Right, very good. Because the altitude will divide the original triangle into two right triangles. And we know how to handle right triangles. We don't know how to handle the general triangles. Do you agree? So that's why the altitude is most important. Okay. And this altitude serves as a bridge connecting two right triangles. It's a very powerful argument here why this is most important. So Rebecca, can you do me a favor? Choose what is the most important in the line? In the circle, right?
Diameter.
Yeah, very good. It's a diameter. Why it's the most important? Well, it's hard to say this. I mean, it's kind of intuitively should be, right? Because the diameter divides the circle into two pieces, two congruent pieces. And there are many other reasons, but this is just very intuitively should be the most important line. So you can see this, okay? We're gonna see, because in this case, we don't know how to argue this, how to argue for the theorem. So since the most important line in the circle is the diameter, what do I do with this proof, case 2?
You can draw one on this circle.
Which one?
You can draw one through A and O.
Right. Because?
This way you can
so.
divide the circle into two congruent pieces.
Right. Not necessarily congruent though, right? Because the C could be anywhere. So it looks congruent, but no, they are not. Okay? The point is that now you see, you reduce your original argument into this, you reduce the question into the two questions which are coming from case 1. Do you see that? Let me call this part as alpha 1. Let me call this as alpha 2, right? Let me call this is theta 1, and this is theta 2. So by case 1, right? Case 1, that theta 1 equal to twice of alpha 1, do we? Theta 2 equal to what? Twice of alpha 2. And therefore, theta, which is equal to theta 1 plus theta 2, that's the central angle, right? Equal to twice of alpha 1 plus twice of alpha 2, which is twice of alpha 1 plus alpha 2. And alpha 1 plus alpha 2 is the measure of the angle BAC. Do you agree? So theta is the angle BOC. You agree? William, are you with me?
Yes.
I have a third case. Can you tell me what is the third case?
Third case is where the angle in this case would be entirely, one part of the angle would be the diameter.
No, that's the case 1, right? Case 1 is that. Emily or Rebecca, what is the third case then?
I'm not sure.
Okay.
Would it be
Emily.
when the angle is
Oh,
between
yeah.
B and C?
That's right. Say it again. Say it again.
When the angle, or when
Yeah.
A is between B and C on the circle.
That's not what I mean here. No. Emily, you don't see this? So this is A here and B here. What is C? C is here. C is missing the diagonal, missing the diameter. So diameter is not in between them. And again, your central angle is here. Right? So your central angle is here. Right? That's your central angle. So this is the case. How do I handle case 3? William.
We could move A.
No, I mean, I don't move. Or you can sliding this around, right? You could, but no. Draw the diameter one more time. Okay, so don't forget the diameter is the most important line. We call this as a D here, okay? Draw this again. And let's look at this. Let me call this angle here as our angle alpha, okay? And let me call this angle here as alpha 1, okay? Now so by case 1, again, the angle alpha plus, so alpha, so the angle BAD, right, is equal to 1/2 of what? BAD. Angle BAD is 1/2 of?
Angle BOD.
Yep, BOD, agree? So the angle CAD is 1/2 of? COD, okay? I mean BOD here, yes? So it's always the half of the central angle, you agree? Yes? CAD is alpha 1, yes? COD is this one. This one is twice of alpha 1. Do you remember that? Yes? Case 1 says the central angle is twice of the inscribed angle. Do you agree? William, are you with me?
Yes.
You are fine, okay? So therefore what? Alpha equal to alpha plus alpha 1 minus alpha 1. Do you agree?
Yes.
Alpha plus alpha 1. Alpha plus alpha 1 is this angle, alpha plus alpha 1. So that's equal to 1/2 of the BOD, agree? Then minus 1/2 of the angle COD there, right? You agree?
Yes.
Now what is that? BOD minus COD. BOD minus COD is BOC there. You agree? Are you with me?
Yeah.
Okay, so that's how you prove this. Is that clear now? In any case, you need to go over this proof yourself. Okay, so these are the 3 theorems we learned today. One is the Pythagorean theorem. The second one is similar triangles. There are 3 equivalent conditions. The equivalent conditions 1 and 2 is well known. But the equivalent condition 3rd is kind of less known. you need to go over the proof, especially when we prove that 3 implies 1, okay? 1 implies 3 is obvious, but there is a gap there, which is 2 implies 3. You should try to do it, okay? And then third theorem today is this inscribed angle theorem, which is very useful, okay? So why this is useful? Let's look at some examples. So look at this, this example. And this is the diameter, right? And this is diameter, okay? So this is the center O there. This is A, B, and C. What is this angle?
In this case, it would be a right angle.
Why it's a right angle?
Because it's the opposite side is the diameter.
Yeah. So that's what the teacher told you, right?
Yeah.
Well,
But why it's a 90 degree? We learned everything we need to make an argument here.
well, it's because angle AOC is a straight angle, which means it measures 180 degrees.
Right. So this angle is the center angle. This center angle is 180 degree. Do you agree? And this is the inscribed angle. So it's it has to be 1/2 of the corresponding center angle. Do you agree? Are you with me?
Yes.
You agree? And so you see that's the reason. Okay, it's not because of anything else. Okay, so let me give you another one. What is the sum of these angles? So this is the 1 point there, okay? So what is the sum of these angles?
$180.
Yep, why?
Because together, like the central angles from each of these angles, they cover the entire circle, totaling 360
Right.
degrees.
Yes, exactly. Because all these, all of the inscribed angles, so the inscribed angles, right? Inscribed angles are A, B, C, D, and E here, right? Covers what?
360.
Right, the entire circle, okay? The entire circle, its center angle is 360, right? 360, and therefore, all these angles are inscribed angle, so adding up, it's just 1/2 of the center angle, you agree? And that's how you use the theorem to see the angles, okay? So you're gonna see some exercises, and later on, I will compile a good set of assignments for you to work on, okay? So I'll see you next time. Do you think that it's understandable, this lecture? Was it okay so far?
Yes.
Okay, very good. So I will make the assignment to you guys, and then I will send you I will send you the link for this recording as well. Okay, so I'll see you next time. Bye bye.
Bye.
Bye, thank
Yep.
you.
Bye bye. Yeah.
Bye.
Yes. Bye.